Imagine standing on a train platform. Around you is a familiar, predictable world. A high-speed express train rushes past. To you, as a stationary observer, the passengers inside that train are in motion. But to them, they are sitting completely still in their seats, drinking coffee, while the entire world outside, including you and the station building, is hurtling backward. This is classical Galilean relativity, something everyone learns in school. It feels intuitive, simple. But in the early 20th century, a young, unknown patent clerk in Bern named Albert Einstein asked a question that would forever shatter this simple picture of reality. He asked himself, what would happen if this train were hurtling not at 100 miles per hour, but approached the absolute, fundamental speed limit of our universe, the speed of light, which is nearly 300,000 kilometers per second? Before Einstein, humanity had lived for centuries in a mental trap constructed by the great Isaac Newton. Newton, who laid the foundations of classical physics, genuinely believed that time was an absolute, rigid, immutable framework of the entire cosmos. In his vision, the universe possessed a hypothetical, divine cosmic clock. It ticked exactly the same everywhere, on Earth, in the scorching core of the Sun, on the frozen fringes of Pluto, and in the absolute dark void of intergalactic space. Time, to Newton, was an independent, straight river, flowing from the past into the future at a constant, fixed speed, and nothing in the cosmos could ever affect its flow. This concept was convenient. It was perfect for calculating the orbits of planets, the trajectory of artillery shells, and the construction of bridges. But it had one fatal flaw. It was fundamentally wrong. Albert Einstein triggered a revolution by proving that time, as an isolated, independent entity, simply does not exist. Time is not a rigid river. It is an elastic, pliable, flexible fabric that is permanently woven with the three dimensions of space: length, width, and height. This is how a terrifying and monumental concept entered physics: the four-dimensional continuum we now call space-time. The most shocking, mind-bending conclusion of the special theory of relativity, formulated in 1905, is this: the faster you move through space, the slower you move through time. Space and time live in a constant, perfect balance. You possess a total speed of motion through this four-dimensional world, and this total speed is always exactly equal to the speed of light. If you are sitting completely still in a chair, all of your speed is spent moving along the time coordinate. You're aging at maximum velocity, but the moment you begin to displace yourself through space, you inevitably steal a portion of that speed away from time. Time, for you, begins to slow down. This is not an optical illusion. It is not a mechanical flaw in a clock's gears, nor is it a biological slowing of cells due to physical stress. The very geometry of reality is changing. To illustrate this paradox, Einstein and his colleagues proposed a thought experiment known today as the twin paradox. Let us break it down in full detail to grasp the sheer scale of this madness. Imagine two identical twin brothers with identical health and the exact same age. One of them, let us call him the astronaut, steps into a hyper-advanced spaceship capable of reaching relativistic speeds. The second brother remains on Earth, at the launch pad, acting as the observer. The ship launches and accelerates to a fantastic speed, 99% of the speed of light. It journeys to a distant star system, turns around, and heads back. What happens at this moment from the perspective of physics? For the brother who remained on Earth, time aboard the receding spacecraft turns into a thick, viscous syrup. If he had a hypothetical, ultra-powerful telescope capable of looking through the ship's viewport, he would see an astonishing sight. The hands of the ship's clock are barely crawling. The astronaut moves around the cabin in an incredibly slowed-down motion, as if in a deep dream. His heart beats once every few minutes. His cells divide dozens of times slower. But what does the astronaut feel inside the ship? This is the core of relativity. To him, everything inside the cabin feels completely normal. His clock ticks at its usual pace. His heart rate is steady. His thoughts flow as always. To him, it was Earth that flew away at near light speed. And it was on Earth that time should have changed. And then the ship lands back on Earth. The hatch opens. The astronaut steps out onto the tarmac. For him, the entire journey by his onboard clock took only 2 years. He is slightly tanned, has a bit of stubble, but is still young and full of energy. But when he meets his brother, he sees a frail elderly man with gray hair and deep wrinkles. For the Earthbound twin, during those same 2 years of ship time, 50 long years had passed. The Earth brother lived an entire life, raised children, and grew old, while his twin took only a few thousand breaths at near light speed. Time was torn apart. It ceased to be a shared experience. This twin experiment might seem like pure science fiction, a grand tale told to secure budgets for space agencies, or a plot for a Hollywood movie. But the reality is, this effect is not fiction. We encounter it every single second when we turn on the navigator in our cars or order a ride through a smartphone app. The Global Positioning System, known as GPS, along with its global counterparts, is direct, tangible proof of Einstein's genius. In orbit around Earth, at an altitude of about 20,000 kilometers, circle dozens of heavy navigation satellites. They continuously broadcast precise time signals down to the planet. For your phone to pinpoint your coordinates within a meter, it must cross-reference the exact time the signal left the satellite with the exact time it was received on Earth. To achieve this, satellites are equipped with ultra-precise atomic clocks, operating on the transitions of cesium atoms. But these satellites are moving around the Earth at an immense speed, about 14,000 kilometers per hour. According to the special theory of relativity, because of this blistering speed, time for the satellites runs slower than for us, standing still on the surface of the planet. This effect steals roughly 7 microseconds a day from the satellite clocks. 7 microseconds is an imperceptible blink of an eye for a human. We cannot notice such a brief window, but for quantum instruments and computer algorithms, it is a colossal value. A light signal travels 300 meters in just 1 microsecond. If the engineers and programmers who built the GPS system had ignored Albert Einstein's formulas and failed to program an automatic time dilation correction into the satellite's onboard computers, it would have triggered a total failure. Within just 24 hours, the navigation system in your phone would begin to miscalculate by several kilometers. After a week, the error would grow to dozens of kilometers, making the system completely useless for logistics aviation, and daily life. We literally navigate our world because we learned to tame the distortions of time. However, speed of motion is far from the only, or even the most powerful way to bend the flow of time, to stretch it or compress it. 10 years after creating his special theory in 1915, Einstein published the general theory of relativity, which opened humanity's eyes to an even deeper mystery. Time can be slowed and deformed by mass, by gravity. To visualize this complex mathematical concept, physicists often use a simple analogy. Imagine a stretched, elastic rubber sheet, like the surface of a trampoline. If this sheet is completely empty, it is flat and smooth. This is a metaphor for empty space-time, devoid of matter. But now, let us place a heavy steel ball into the center of this sheet, say, weighing several dozen kilograms. This ball represents a massive cosmic object, a planet, a star, or an entire galaxy. Under the weight of the ball, the rubber sheet inevitably sinks, forming a deep well with sloping sides. If you roll a small light marble along the edge of this sheet, it will not travel in a straight line. It will begin to spiral around the heavy center, gradually sinking toward it. From the outside, it looks as though the heavy ball is pulling the light one toward itself. This is what Einstein called gravity. Gravity is not an invisible force of attraction as Newton thought. It is simply geometry. The warping, the deformation of space itself. But the most astonishing part is that the heavy ball does not just warp spatial coordinates. It warps, deforms, and stretches the coordinate of time itself. The fabric of time warps right along with space. The closer you are to the source of a powerful gravitational field, the more time stretches. The slower it flows relative to objects far away from the well. This phenomenon is called gravitational time dilation, and it is happening right now as you listen to these words. Our planet Earth possesses mass, which means it warps the space-time around it. If you live on the ground floor of an apartment building or at the very base of a tall mountain, you are physically closer to the center of Earth's mass. The gravitational field here is slightly stronger, which means time for you flows just a fraction slower than for people living in penthouses or working in high-altitude observatories. Of course, given Earth's relatively modest mass, this difference is microscopic. Over an entire 80-year lifespan on the ground floor, you would gain only a fraction of a billionth of a second over someone living in a penthouse. You will not look visually younger. Your biological clock will never notice. But this fact has been proven flawlessly and repeatedly, using portable atomic clocks carried to mountain peaks and lowered into deep mines. Earth is a real, albeit incredibly weak, time machine. But what happens if we journey deep into space and find an object whose mass exceeds Earth's, not by billions, but by trillions of times? An object compressed to such a degree that its gravitational well becomes infinitely deep, literally tearing the fabric of space-time? We are approaching the boundary where Einstein's physics begins to unravel, and where time does not just slow down, it completely swaps places with space, turning from an abstract concept into a physical destination. We stand on the threshold of the greatest gravitational monsters in the universe, at the event horizon of black holes. But that is for the next part of our film. In our journey through the cosmic fabric, we have seen how speed and the mass of planets can warp the passage of time. But these are gentle ripples, mere scratches on the surface of reality. To see time truly shatter, we must turn our gaze toward the most terrifying remnants of dying giants. We must look at the birth of a black hole. Imagine a star 20 or 30 times more massive than our sun. For millions of years, this giant lives in a state of violent yet perfect equilibrium. Deep within its core, a ferocious nuclear furnace burns, fusing hydrogen into helium and helium into heavier elements. This cosmic fire creates an immense outward pressure, a brilliant force pushing against the star's own crushing gravity. It is a cosmic tug-of-war that keeps the star alive, but a star's fuel is finite. Eventually, the furnace runs out of elements to fuse. It reaches iron, the dead end of nuclear fusion. Fusing iron requires more energy than it releases. In an instant, the cosmic fire goes out. The outward pressure vanishes, and gravity, unchecked, ruthless, and absolute, wins the war. What follows is one of the most violent events in the universe, a supernova explosion. The outer layers of the star are blasted into space in a brilliant flash of radiation, but the core, the trillion-ton heart of the giant, collapses inward. It falls into itself with unimaginable speed. If the remaining mass is large enough, nothing in the known universe can stop this collapse. Not the repulsion of atoms, not the pressure of subatomic particles. The core shrinks past the size of a planet, past the size of a city, past the size of a single atom. It condenses into a region of space so small and so densely packed with matter that the gravitational well it leaves behind becomes a bottomless pit. The rubber sheet of space-time we discussed earlier doesn't just sag, it is punctured. A black hole is born, and with its birth, the rules of time change forever. Every black hole is surrounded by an invisible, mathematical boundary, a point of no return, known as the event horizon. It is the exact perimeter where the escape velocity of the black hole equals the speed of light. Since nothing can travel faster than light, nothing, not even a beam of photons, can escape once it crosses this line. It is a one-way trapdoor in the universe. But the most mind-bending property of the event horizon is what it does to time itself. To understand this, let us perform another classic thought experiment. Imagine our astronaut twin from earlier, but this time he is on a tragic mission. He has volunteered to plunge directly into a supermassive black hole. His brother remains far away, safe inside the mothership, watching the descent through a telescope. As the astronaut fires his thrusters and drifts toward the pitch-black sphere of the horizon, a strange, haunting asymmetry occurs between the two brothers. For the brother watching from the safe ship, the falling astronaut begins to slow down. As the astronaut approaches the invisible boundary of the horizon, every movement he makes takes longer and longer. He raises his hand to wave, but to his brother, the gesture takes hours, then days, then weeks. The gravity near the horizon is stretching the space-time fabric so violently that the light waves carrying the image of the astronaut are stretched out, losing their energy. The astronaut appears to turn deep orange, then dark red, fading into absolute obscurity. To the outside world, the astronaut will never be seen crossing the event horizon. He will appear to freeze at its edge, hovering there forever, like a ghost trapped in amber, a permanent monument frozen in time. But what does the falling astronaut experience? To him, there is no freezing. There is no delay. His watch ticks normally. His heart beats steadily. As he drifts toward the horizon, he looks back at the universe he is leaving behind. Because gravity slows his time relative to the outside world, he sees the entire future history of the cosmos accelerate before his eyes. He watches galaxies collide, stars burn out, and universes age in a matter of seconds. And then, without feeling any sudden barrier or cosmic wall, he passes through the invisible threshold. He crosses the event horizon. He is inside. Once you step over the threshold of the event horizon, the universe as you know it undergoes a radical, terrifying inversion. In our daily lives, space and time are fundamentally different. Space is a realm of freedom. You can choose your direction in space. You can walk left, you can turn right, you can stand perfectly still. Time, however, is a prison. You cannot stop your march into the future. You cannot turn back to yesterday. But inside a black hole, Einstein's field equations reveal a shocking mathematical secret. The coordinates of space and time swap their signs. They trade places. Inside the event horizon, space becomes your prison and time becomes your direction. Think about what this means. Outside the black hole, the center, the singularity, is a physical location in space. It is a point you can point your finger at. But once you cross the horizon, that center is no longer a place. It becomes a moment in time. It becomes your absolute, unavoidable future. Just as outside a black hole, you cannot stop yourself from traveling into next Monday. Inside a black hole, you cannot stop yourself from moving toward the center. No matter how powerful your rocket engines are, no matter which direction you steer your ship, every path, every choice, and every dimension points to only one coordinate: the center. Trying to escape a black hole by flying backward makes as much sense as trying to escape tomorrow by running backward. The geometry of space-time has twisted into a closed loop. The past has been erased, and the future consists of only one thing: the singularity. At the very center of this gravitational trap lies the ultimate destination, the singularity. According to general relativity, all the mass of the collapsed star, millions of times the mass of our Earth, has been crushed into a point of zero volume. An infinitely small dot in space. If you divide finite mass by zero volume, the math produces a terrifying result: infinite density, infinite gravitational pull, infinite curvature of space-time. At this point, the fabric of the cosmos is stretched so tightly that it snaps. The singularity is not an object made of matter. It is a place where space and time simply cease to exist. It is the edge of the world, the absolute end of the cosmic screenplay. And here, modern science faces its greatest crisis. When physicists try to calculate what happens at the singularity using Einstein's theory of gravity, the equations break down. They give answers of infinity, which means the theory no longer works. It is blind. To fix this, we need to use quantum mechanics, the science of the ultra-small. But when we apply quantum equations to the singularity, they conflict with gravity, the two pillars of modern physics, theories that work flawlessly in every other part of the universe. Look at the center of a black hole and call each other liars. The singularity is a locked vault, hiding the ultimate secret of existence. It is the place where gravity and the quantum world meet, where time dies, and where something entirely new must begin. What lies beyond this breakdown of physics? To find out, we must look at what happens when the universe tries to heal itself through the quantum secrets of the vacuum. But that is for the next part of our journey.